Hello viewers, today in this program we will discuss a very important topic of the mathematics, namely partial differentiation. You might be having knowledge of simple differentiation, ordinary differentiation. The differentiation is defined as rate of change of one variable with respect to another variable. Now we will define the partial differentiation. For a function of two or more independent variable, normal differentiation is not applicable. However, if any one of the independent variable is taken and it is assumed that it is the only independent variable of the function and all other independent variables remain unchanged, then the function can be differentiated with respect to that independent variable. The differentiation in this process is called partial differentiation of the function. For a function of two variable, the partial derivatives are defined as follows. Let f be a function of two independent variables x and y defined in some region R. The derivative of f with respect to x, called the partial derivative of f with respect to x, and it is denoted by f x or del f over del x. Thus, the del f over del x is given by del f over del x is equal to limit h tend to 0 f of x plus h comma y minus f of x y divided by h. This is representing the rate of change of a function with respect to x while y is keep constant. Similarly, the derivative of f with respect to y, assuming that x is constant if it exists, is called the partial derivative of f with respect to y. It is denoted by f y or del f over del y. This is given by del f over del y is equal to limit k tend to 0 f of x comma y plus k minus f of x y upon k. It represents the rate of change of f with respect to y while x is kept constant. The partial derivative of a function of three or more variable are defined in similar manner. For example, now I am explaining the example related to the partial derivatives of the function of two variable. Here u is log of x square plus y square, then its partial derivative del u over del x is given by 1 upon x square plus y square multiplied by 2x. Here we have obtained the derivative of the given function keeping y constant, and similarly del u over del y is equal to 1 upon x square plus y square multiplied by 2y. Here we have kept x as constant. Another example representing the third order derivative, if u is e to the power x, y and z, it is the function of three variable x, y and z, then find the value of del cube u over del x, del y, del z, that is the partial differentiation with respect to z, then with respect to y, then with respect to x. Its solution is as follows. Del u over del z is e to the power x y z multiplied by x y. Here x and y both are treated as constant. Then del 2 u over del y del z can be obtained as del over del y of del u over del z, that is equal to del over del y of e to the power x y z multiplied by x y, that is equal to e to the power x y z multiplied by x plus e to the power x y z multiplied by x y multiplied by x z, that is equal to e to the power x y z multiplied by x plus x square y z. Then the third order derivative del cube u over del x del y del z, that is equal to del over del x of del 2 u over del y del z. This is equal to del over del x of e to the power x y z multiplied by x plus x square y z, that is equal to e to the power x y z multiplied by 1 plus 2 x y z plus e to the power x y z multiplied by x plus x square y z multiplied by y z, and hence it is equal to e to the power x y z multiplied by 1 plus 3 x y z plus x square y square z square. Now, I am going to explain you some special function categorized as homogeneous function, and we will discuss a very important property of the homogeneous function with Euler theorem. A class of function for which the sum of power of independent variable in each of the term is same is homogeneous function. The homogeneous function may also be defined as follows: a function f x y in two variables x and y is said to be homogeneous function of degree n if it can be expressed as in either of the form x to the power n phi y by x, that is x to the power n multiplied by some function of y by x, or y to the power n multiplied by some function of x upon y, where n may be any real number. This function is homogeneous function. Now, I will explain you the important theorem related to homogeneous function called Euler theorem for homogeneous function. If u x y is homogeneous function of degree n in two independent variables x and y, then x del u over del x plus y del u over del y is equal to n u. The proof of the theorem is as follows: the homogeneous function u can be rewritten as u is equal to x to the power n phi y by x. The partial differentiation of u with respect to x and y are given as del u over del x is equal to x to the power n phi dash y by x multiplied by y upon x square negative plus n x n minus 1 phi y by x, and del u over del y is equal to x to the power n phi dash y by x multiplied by 1 upon x. Multiplying the equation 1 with x and equation 2 with y and adding, we find x del u over del x plus y del u over del y is equal to nu. Hence, prove the theorem. Now, I will explain the example related to Euler theorem. If u is equal to sine inverse x square y upon x plus y, then show that x del u over del x plus y del u over del y is equal to 2 tan u. The solution of this problem is as follows: write v for sine u. V is equal to sine u, then del v over del x is cos u, and del u over del x and del v over del y is equal to cos u del u over del y. Now, v is equal to sine u, that is equal to x square y upon x plus y, that can be represented as x to the power 2 phi y by x, that is, it is the second order homogeneous function of two variable x and y. It is homogeneous function of degree 2. Hence, by Euler theorem we have x del v over del x plus y del v over del y is equal to 2v. Putting the value of v and del v over del x, del v over del y, we find x cos u del v over del x plus y cos u del u over del y is equal to 2 sin u, or x del u over del x plus y del u over del y is equal to 2 tan u, hence prove the theorem. Now, I will explain you another example which represents important deduction of Euler theorem. It is the example u is equal to x cube plus 2 x square y plus y cube whole raised to the power 3 by 2, then show that x square del 2 u over del x square plus twice x y del 2 u over del x del y plus y square del 2 u over del y square is equal to 63 by 4 multiplied by x square plus 2 x square y plus y cube whole raised to the power 2 by 3. Its solution is as follows: u is equal to x cube plus twice x square y plus y cube whole raised to the power 3 by 2 can be represented in the form of homogeneous function as x to the power 9 by 2 multiplied by 1 plus 2 y by x plus y by x whole raised to the power 3 whole raised to the power 3 by 2. That is the homogeneous function of degree 9 by 2 multiplied by function of y by x. It is a homogeneous function of x and y of degree 9 by 2. Therefore, using Euler theorem, we find x del u over del x plus y del u over del y is equal to 9 by 2 multiplied by u. It is the equation 1. Now, we will differentiate partially this equation 1 with respect to x and y. Here the differentiation 1 partially with respect to x, we find x del 2 u over del x square plus del u over del x plus y del 2 u over del x del y is equal to 9 by 2 del u over del x. While differentiating with respect to x, we kept y constant, but u and del u over del x are both function of x and y, therefore differentiating them. Similarly, differentiating 1 partially with respect to y, we find x del 2 u over del x del y plus y del 2 u over del y square plus del u over del y is equal to 9 by 2 del u over del y. These are the equation 2 and 3. Now, we will multiply 2 with x and multiply 3 with y and add the result. We find x del 2 u over del x square plus twice of x y del 2 u over del x del y plus y square del 2 u over del y square, which is equal to 9 by 2 multiplied by x del u over del x plus y del u over del y minus x del u over del x plus y del u over del y. Using the result 1 here, that is x del u over del x plus y del u over del y is equal to 9 by 2 u, we find x square del 2 u over del x square plus twice x y del 2 u over del x del y plus y square del 2 u over del y square is equal to 9 by 2 multiplied by 9 by 2 minus 1 multiplied by u, that is equal to 63 by 4 u, that is 63 by 4 multiplied by x square plus twice x square y plus y cube whole raised to the power 2 by 3, hence prove. Now, I will explain you an important concept of partial differentiation, that is Jacobian. If u and v are two differentiable function of independent variables x and y, then the determinant value of the partial derivatives of u and v with respect to x and y as follows. In the determinant, we have put del u over del x and del v over del x in first row and del u over del y, del v over del y in the second row and find the value of the determinant, it is called Jacobian. That is also the transformation of u and v with respect to x and y. It is represented by j, and it is also represented as del u v over del x y. The Jacobian for the function of 3 or more variable is defined in similar manner. If we have 3 variable u, v and w associated with x, y and z, it is 3 by 3 determinant having 9 partial derivatives. Now, I will discuss an important deduction of Jacobian, that is called chain rule for Jacobian. Suppose p and q are differentiable function of u and v, where u and v themselves differentiable function of independent variable y and z, and u and v are linearly independent, then del p q over del x y is same as del p q over del u v multiplied by del u v divided by del x y, that is chain rule of the Jacobian. The proof of chain rule of Jacobian is as follows. Applying chain rule of differentiation, partial differentiation over the p and q, we find del p over del x is equal to del p over del u over del x plus del p over del v over del x. Similarly, del p over del y is equal to del p over del u over del y plus del p over del v over del y, and del q over del x is equal to del q over del u over del x plus del q over del v over del x. Similarly, del q over del y is equal to del q over u multiplied by del u over del y plus del q over del v multiplied by del v over del y. Therefore, we get del p q over del x y is equal to the determinant value of del p over del x, del p over del y in first row, and del q over del x, del q over del y in second row. Its determinant value can be represented as the determinant del p over del u multiplied by u over x plus p over v multiplied by v over x. Similarly, p over u multiplied by u over y plus p over v multiplied by v over y, and q over u multiplied by u over x plus del q over v multiplied by v over x, and del q over u multiplied by del u over y plus del q over v multiplied by del v over del y. This determinant can be expressed as the product of the two determinants as follows: del p over del u, del p over del v in first row, and q over u, q over v in second row. In the second determinant, we have u over x and u over y in first row, v over x and v over y in second row. Therefore, this represents the product of two Jacobians. First is del p q over del x u v, and second is del u v over del x y. Hence, prove the chain rule of the Jacobian. Example representing Jacobian is as follows. If x is equal to r cos theta and y is equal to r sin theta, that is x and y are function of r and theta, then evaluate the partial derivative x y del x y over del r theta, that is Jacobian x y over r theta, and hence find the Jacobian r theta over x y del r theta over del x y, and also verify that del r theta over del x y is reciprocal of del x y over del r theta. The solution of this problem is as follows. We have the x is equal to r cos theta and y is equal to r sin theta. Therefore, del x over del r is equal to cos theta, del x over del theta is equal to minus r sin theta. Similarly, del y over del r is equal to sin theta, and del y over del theta is equal to r cos theta. Therefore, the Jacobian del xy over del r theta is equal to the determinant value cos theta minus r sin theta r cos theta, which gives the value equal to r. R and theta can be expressed in terms of x and y as follows: r square is equal to x square plus y square and theta is equal to tan inverse y by x, that is r and theta are function of x and y. Therefore, on differentiation 2r del r over del x is equal to 2x, hence del r over del x is equal to x upon r. Similarly, del r over del y is equal to y upon r. Del theta over del x is equal to 1 upon 1 plus y by x whole square multiplied by minus y upon x square, that is equal to minus y upon r square. And similarly, del theta over del x is equal to 1 upon 1 plus y by x whole square multiplied by minus y by x square, that is equal to minus y upon r square. Therefore, the Jacobian value del r theta over del xy is given by the determinant value x upon r y upon r in first row and minus y upon r square x upon r in the second row, that is equal to 1 upon r cube multiplied by the determinant value x y y x, that is equal to 1 upon r when simplified. Thus, the result is verified. Now, I will explain you the functional independence and dependence using the concept of Jacobian. Suppose u x y and v x y are two differentiable functions of two independent variables x and y. These functions are said to be functionally dependent if their Jacobian value is equal to 0. This is necessary and sufficient condition for interdependence between u and v. If j is not equal to 0, then u and v are said to be functionally independent. In similar manner, dependence of function of 3 or more variables can be discussed. Example showing the dependence: if u is equal to cos inverse x plus sin inverse y and v is equal to x root 1 minus y square minus root 1 minus x square, determine whether u and v are functionally dependent. Solution of this example, this problem is as follows. We have u x, that is partial differentiation of u with respect to x, is equal to 1 upon root 1 minus x square with negative sign. Similarly, del u over del y is equal to 1 upon root 1 minus y square and del v over del x is equal to root 1 minus y square plus xy upon root 1 minus x square and del v over del y is equal to minus xy upon root 1 minus y square minus root 1 minus x square. Therefore, the Jacobian value del u v over del x y is expressed as the determinant value minus 1 upon root 1 minus x square and 1 upon root 1 minus y square in first row, and in the second row root 1 minus y square plus xy upon root 1 minus x square and minus xy upon root 1 minus y square minus root 1 minus x square. When we solve this determinant, we find xy upon root 1 minus x square 1 minus y square plus 1 minus xy upon root 1 minus x square 1 minus y square. that becomes 0. Therefore, u and v are functionally dependent. Today in this lecture, the concept of partial differentiation has been discussed. The definition of first and second order partial differentiation has been given and explained with example. Then homogeneous function and Euler theorem related to homogeneous function has been discussed and an important deduction have been derived. This theorem is also verified for a given homogeneous function. And in the end of lecture, an important concept of function dependence using the concept of Jacobian has been discussed. I hope you all enjoy the lecture. Thanking you.